Okay, so looking at the notes, let's continue. Um, Momentum is conserved is the next topic over here. It says here though, if momentum is conserved, and what does the word conserved mean? Right? Conserved, if you're going to conserve something, you're going to save it, you're going to hold on to it. Um, Same thing here. If I conserve it, kind of like the law of conservation of mass. Whatever mass I started off with equals the amount of mass afterwards. It's conserved. I'm holding on to all of it. I'm going to keep it all. Okay, so momentum it's conserved. It says here, and it says it does not change. How could someone decrease the force at which they are hit in a collision? Okay? So, for this to occur, for this to happen, which could happen, even though the amount of momentum before the hit is going to equal the amount of momentum after the hit, to decrease the amount of force, which is 100% possible, we can do this by increasing the amount of time to stop. And that's what we talked about up here. Okay? If I can increase that stop time, and that's the reason for the crumple zones and seat belts and airbags, so that way we can decrease the amount of force. Now, does that only occur in car wrecks? No, it occurs in a lot of other things in life. Okay, so here's a few examples. They're going to give us an example here. It says a boxer. So a boxer rides the punch. So riding the punch. What does that mean? It says here, fans of boxing frequently observe this same principle of minimizing the effect of a force by extending the time of collision. I mean, you're a boxer, you know your face is about to get punched. And in their mind, they need to think that they need to increase the time of that collision to decrease the amount of force that they're going to have on their face. It says here, though, when a boxer recognizes that he's about to get hit in the head by his opponent, the boxer often relaxes his neck to allow his head to move backwards upon impact. In the boxing rule, this is known as riding the punch. A boxer rides the punch in order to extend the time of impact of the glove with their head. Extending that time results in a decrease I think I'm off. Am I off a little bit? I think I am. I apologize. Hold up. Extend the time results in a decrease the force. In decreasing. That's what it is. I apologize. The force. And thus minimizes the effect of the force of that collision onto their face. Okay? So let's keep going. Next one, it says here, merely increasing the collision time by a factor of 10 would result in a tenfold decrease in that force. Now that's what physics is in action. That's what it says here. Well, let's keep going. Example B. It says airbags and in a car collision. When encountering a car collision, right, when you're going to get into a car wreck, it says here that the driver and passenger tend to move in accordance with Newton's first law of motion. That we know. If the car is traveling 60 miles an hour, your body is also traveling 60 miles an hour due to Newton's first law of motion. It says here, though, that their motion carries them towards the windshield. That results in a large force exerted over a short amount of time in order to stop their momentum. It says here, though, if instead of hitting that windshield, the driver and the passenger hit an airbag, for an example, then the time duration of the impact is actually going to increase when hitting an object with some given such as an airbag. So when you hit that airbag, the airbag is not like a hard, brick wall. It has some give with it. That's what they're trying to say there, which is going to increase that time duration by a factor of 100, which increases the time here. That's going to cause a decrease in force on your body. Okay? I mean, the last thing you want is, to be hitting something so hard like a brick wall that instantly stops you. In that case, we decrease the amount of time, we increase the amount of force on your body. But to do the opposite, which is completely possible, all right, not only do we wear seat belts, we also have airbags, and we have side airbags for the back passenger. Then we now have what we call over here the crumple zone in the front as well as the back of the car. All of that combined helps us to increase the stopping time on our body, so that way we can decrease the amount of force on us, right? I know some of us, we may have that misconception that cars are just made like super cheap out of plastic nowadays. But they're made like that with an intention to help save your life, okay? Again, like I said, some people, yes, they had the seatbelt and yes, they have an airbag, but still they weren't surviving car wrecks because even though their body came to a stop, their organs internally were still going 60 miles an hour, and your organs, slammed inside and got ripped apart and messed up because of that hard collision. So this helps to decrease the force on your body. It says here's a couple of other examples too that we have. It says the padding in helmets. Oops. Why do we have padding? Not just football helmets, hockey helmets, baseball helmets. We have padding inside of there because what if you get into a collision? What if you're a baseball player and the ball is coming 92 miles an hour and it's going straight towards your head? It's still going to hurt with that helmet on, but the padding in there is going to help increase that stop time on your head, so that way they can decrease the amount of force that's going to occur to your brain or to your head. Okay? Also, it says here padding on dashboards. So the next time you get in the car, whether you're the passenger or whether you're the driver, the dashboard that's in front of you, push down on it as hard. Push down, like really give it a good push. And you're going to see that there's padding under there and it has a little bit of give to it. Even the dashboards is made of padding to help increase the stop time, so that way we can decrease the force on your body. And then the next one here we call is follow through. Follow through is important though. If you play baseball, if you play tennis, if you play golf, there's a lot of sports when it comes to follow through. Okay, so let's go ahead and talk about that one. It says here though, in rackets and bats and golf sports and all other sports, hitters are often encouraged to follow through when hitting or striking at a ball. High-speed films, it says here, of the collisions between the bats and the rackets and the balls have shown that the act of following through serves as an increase in the time over which that a collision occurs. So if you've ever played baseball, softball, golf, you've probably had coaches and parents yelling at you about you need to follow through. You need to follow through with that hit. This is what we're talking about here. This is what they mean. When you're following through with that, for an example, baseball bat, you're increasing the amount of time that the collision of the bat and the ball are having together. It says here, though, that this increase in time must result in a change in some other variable. So if I change the variable of time, I'm going to cause another variable to change as well. It says here, this is what we call impulse momentum. This increase, where am I at? Right here. Change theorem. surprisingly, the variable that is dependent upon the time in such this kind of situation is not force. So when we're talking about follow through, and you're talking about it in sports, it's actually not the force that is the other variable that's affected. When I increase the amount of time, it's not the amount of force that's going to be decreased, right? Because that's what's happening over here. That's what's happening over here. But in this situation, when I increase the collision time between the bat and the ball, I am not affecting the force. The force in hitting is dependent upon how hard the hitter is going to swing that bat or the racket or golf club, not the time of impact. Instead, the follow through increases the time of collision, and then it's going to contribute to an increase in the velocity of that ball. So if you're a baseball, softball player, for an example, and the coach, parents, everybody's yelling at you, you need to follow through with that bat. Okay, what they mean is if you increase the amount of contact that the bat and the ball are going to have, then you're going to cause something else to change. What is going to change? Well, it's not the force that's going to change. It's actually going to increase the velocity. And let's go back, because velocity and time are in an equation that we've talked about before in the past. Okay, so let's come back over here. And here's my baseball player, right? And so if he swings his bat, and if he was to stop his bat at this point right here versus swinging all the way over here and following through, then the ball is not going to go as far. Okay, you've probably heard that before. But the reason why is because as you swing all the way through, all right, so here's the bat and the ball, you're increasing the amount of time that the bat and the ball are having contact with each other, which is now going to cause the velocity change. And when the velocity changes, we had this equation on first semester, V equals D over T. If velocity changes because you changed the time, then that's going to cause an increase in the distance, right? V equals D over T. And now you're going to hit that ball further. If you play golf, same thing. I don't care if that golf ball is not moving. That golf ball is there on the tee, not even moving, right? So when you hit that golf club to the golf ball and you have contact, the same thing as well. We want to increase the amount of contact time, which is then going to cause the velocity change. And when the velocity changes, then the distance that that ball is going to travel is also going to change. Why? Because of the amount of time. It has nothing to do with force. It has nothing to do with, look at this right here, how hard you're going to hit it. Let's go back to baseball. All right. Let's find, you think about some of these baseball players, and some of them are really small, right? Some players are not very tall. They're not very, huge and big, right? Some of them are very short and small. But how in the heck can a small baseball player, because some of you in this class are probably taller than some baseball players out there, but yet they can hit home runs? How is that possible? I mean, what, they're going to hit it harder? No, they're already given everything that they can. It's not like, oh, okay, I got up there the first time and I just, I kind of hit it. No, you're, MLB, you're not going to just hit it. You're going to actually go out there and you're going to give it everything you got. So are they going to go and give it more if you're already giving 100%? I mean, mathematically, that's not possible to give 110%. So if you can only give 100% because that's all you can give, then what else can you do that's going to change that bat and the ball? What can you do? You can increase the amount of time that the contact is occurring between the bat and ball. And when that occurs, then the velocity is going to change. Because velocity changes, the distance also changes because they're all within the same equation. V equals D over T. Okay. And so that's what I think your coaches and your parents are trying to tell you when they're screaming and yelling at you. Okay. So the next time that comes up and that happens and you get told you better follow through, you can go ahead and let them know. Do you mean increase the amount of contact between the ball and the bat so that way I could increase the velocity? And when that velocity changes, then it's going to cause the distance of that ball to go. That's probably what they mean. They're probably going to look at you a little crazy though, too. That's okay. Let's keep going. Here's a couple of questions. The more time a force is applied, to the object, then the force will decrease. The less time, if I decrease the amount of time to stop the object, like in a car wreck, then the force is going to actually increase, right? You slam into a brick wall, that hurts. Number 3, the larger the force, the more momentum it has. The slower the object, the less momentum it has. And if I want a smaller force to be exerted on my body during a collision, I should take more time to stop. Right? And that's the reason for the seat belts and all these airbags and stuff nowadays, is to try to increase the collision time. Alrighty, let's keep going with our notes. So, conservation of momentum. On this page, we are going to need the color. Well, you know what? We can do those in class. We'll skip one part of it, and we'll do that part in class. Conservation of momentum. Momentum, it says here, though. Got to find my notes. Momentum is conserved, and that's what we just talked about on the previous page. During collisions, kind of like the conservation of mass. The amount of mass I have before is the amount of mass I have afterwards. The amount of momentum I have before the collision equals the amount of momentum I have after the collisions. It says here that this means that the amount of momentum in a closed system before a collision is equal to the amount of momentum in a closed system after the collision. You probably did, or there's a good chance, if it wasn't last year in chemistry class, it might have been like in middle school, where you get vinegar and you get baking soda. And you can put those two into take the mass of them both, then go ahead and mix them, and take the mass after the chemical reaction occurs. Then the mass is not going to equal each other. You're probably going to end up with less. But that's because that's what we call an open system. Then you do the same experiment, which again, you may have done it in chemistry. Maybe you took IPC. And in that case, then the second time around, you had vinegar and you had baking soda, but you put both of them in a Ziploc baggie and you zipped it up. So no air is coming in, no air is coming out. Your teacher probably even told you, go ahead and push as much air of it out as you can right now. You took the mass before, you took the mass after the chemical reaction occurred, and the mass was pretty much the same. And that was because after the gas production, it was in a closed system where it did not get to be released out, and you were able to conserve all of that mass. Okay? Now, same thing here. If I'm having a collision occur in a closed system, the amount of momentum I have before equals the amount of momentum I have afterwards. But unfortunately, we live in this world where pretty much everything is in an open system, right? I really can't conserve it. There's all this friction and other things around us where energy transformation is always occurring. But for our class, though, it says here, this year, we will only be talking about what we call closed systems, right? In that perfect world environment. But we need to know that there's actually two types of systems, open and closed, okay? But in that perfect world, we like to consider it to be a closed system. It says here, though, an open system is a situation where things can be exchanged, right? I gave you that example. If you were in chemistry class and you mixed those, you had a beaker of vinegar and a small little container of baking soda, you mix them together, then the gas bubbles are going to release into the air, and it's an open system where the gas from the container release and exchanged with the air around you or the environment. It says here that this is more like what real world situations are. Now, a closed system is where nothing is exchanged with the environment. So everything inside is conserved. A closed system would be like, for an example, the U.S., if we made all of our own products, right? We no longer bought from other countries cars and TVs and cell phones and clothes. If we made our own cars and TVs and cell phones and clothes and everything and only bought within the U.S., that would be a closed system, all right? So let's keep going. Now let's talk about the different types of collisions, because we've been using that word collisions, and some of us may be thinking, oh, okay, car wrecks, or oh, maybe she talked about like a boxer, and so they got hit in the face, and that was the collision. Well, there's different types of collisions, and there's actually 3 basic types of collisions that we're going to talk about, okay, and that we need to know. So the first type of collision is what we call a elastic collision. Let me go ahead and write that in. Elastic collision. Second type of collision is what we call an inelastic collision. Inelastic collision. The third type is what we call an explosion. I know that sounds like, what? That's like the opposite, Miss Munson. And it kind of is. Explosion. But it's considered to be within our collisions. Okay. So let's go ahead and let's take a look at this. Elastic collisions. It says these are collisions where things hit each other and then they actually bounce off. Alrighty. So for an example, it says here though, or what happens is that you start off, or you start with 2 objects and you end up after the collision with 2 objects. So for an example, playing bowling, right? You get that bowling ball and it rolls down the lane and collision with the bowling pins. Does the bowling ball stick to the bowling pins? No. They bounce off of each other. That's what we call an elastic collision. Let's think of another example. What about the baseball bat and the bat? All right, the ball and the bat. The bat hits the ball and then the ball goes flying. All right, they didn't get stuck to each other. That's an elastic collision. Playing tennis, playing golf, playing pool, just getting a regular tennis ball and throwing it against your wall and it bouncing back at you is an elastic collision. All right, let's keep going. Now, an inelastic collision is collisions where things are actually, they hit each other and then they actually stick together. It says here though, you actually start off with 2 objects and you end up with 1 object. So an example would be they have a fish here and he's swimming and here's a little fish and he eats him, right? He eats him. And now the little fish is in his stomach, right? You start off with 2 things and you end up with 1. We've got 2 astronauts in outer space and they're going towards each other. And once they do, they hold on to each other. Now we started off with 2 and now they ended up as 1. Okay. So from 2 to 1 is what we call an inelastic collision. Now explosion though, it says here, which is pretty much the opposite of what collisions are, is where events that you actually start off with 1 object and they break, or it breaks into multiple. And we're using the word multiple because, I mean, heck, it can start off with, I was holding this glass plate and I was washing dishes. I dropped it on the floor and that one glass plate broke it into 28 pieces, multiple parts. Okay, now for the type of equation here, when it comes to explosion, every single multiple part has to be accounted for mathematically. Okay, so if we have one object that broke into 7, then now we have to mathematically include all 7 parts into this equation. Okay, here we have 2 parts on one side, we end up with 2 parts. Those are the 2 parts that we have to include into the equation. Here, I start off with 1 part and then I end up with 2 parts. I need to account for both of those parts because that's what it ends up at. And then again over here, however many pieces it breaks into, I have to count them all up and mathematically they all have to be into my equation. So we can have a 7-part equation if need be. Okay? And it says here that you actually start off with 1 object and you end up with 2, and I'm going to go ahead and just put right here, or more objects. Okay? It could be 2 or more objects. Alrighty. This part over here, I'm going to leave it blank. We're going to come and do this together in class. Okay? But I'm not going to do it right now. Let's keep going in our notes for a little bit longer, and let's try to get through another page or so. Alrighty? And then I'll post this part. So it says here net momentum. Well, I'm going to do this part. I'm trying to see if I can, let's see. Yeah, I think I could. Okay, let's keep going. So here we've got 2 soccer balls. And it says both soccer ball has a mass of 0.47 kilograms. Kilograms is the exact SI unit that I need, so do not convert or change it. Now, both of them are moving east. All right, so that would be this ball moving east, and this ball is also moving east. They're both moving in that direction. It says here, though, that soccer ball A is moving faster than soccer ball B. Okay, so soccer ball A is moving faster than soccer ball B. Soccer ball A has a velocity of 0.84 meters per second. I'm going to put 0.84 for A. Soccer ball B has a velocity of 0.04 meters per second. Calculate the total momentum for both the soccer balls. Okay, so right now on these 2 equations, we're going to do this conservation of momentum, but we're going to start off by breaking it down from part to part to kind of simplify it a little bit. So let's start off with the initial momentum of ball A. So I know, I'm going to go ahead and write it over here. P equals M times V, because that's the equation I need. So the momentum for a soccer ball A is 0.47 times the velocity 0.84. Multiply those 2 numbers together, double check my math. I got 0.39. What is my SI units? Kilograms times meters per second. Now let's do momentum of soccer ball B. Again, it has the same mass of 0.47, but the velocity is 0.04. Now let's go ahead and multiply those, but please go ahead and double check my math. And I got 0.02 kilograms times meters per second. Okay. Now the total net. Oh my goodness, I've had students ask me before, and I know we said about this. What does the word net means? The word net is the same thing as the word sum. Okay? And mathematically, if we were using that word sum, it's the same thing as the word total. Or I'm going to put add. Okay? So if you see the word net, or you see the word sum, or see the word total, you need to add them together. Okay? Mathematically, that's what you're going to do. So let's go ahead and find the net momentum, or add the momentum of both balls before the collision. Okay, so 0.39 plus 0.02 comes up to 0.41 kilograms times meters per second. Not bad. Actually, this is only one part of the equation. This together, this whole top part, is one full equation, but we're starting off by breaking it piece by piece. Now, when the soccer ball A catches up to soccer ball B because it's moving faster, the two soccer balls actually collide. Now, the collision causes soccer ball A to stop. Wait a minute. If my object comes to a stop, what is the velocity? 0. So I'm going to go ahead and write that down over here. This is still soccer ball A, and that's soccer ball B. Okay. Now, soccer ball B starts to accelerate 0.88 meters per second. 0.88. Let's go ahead and find the momentum of soccer ball A and soccer ball B. Let's do that. We know P equals M times V is my equation. So for soccer ball A, we know the mass. It's up here, 0.47. What is the velocity? 0. So remember I said earlier in the beginning of the notes, for momentum, you could have a 0 as an answer. Why? Because the only way to have momentum is if the object is moving. If my object is not moving, then there is 0 momentum. So my actual answer comes out to 0 kilograms times meters per second. What is the final momentum for ball B? Well, it has the same mass, and the velocity is 0.88. So when I multiply those two numbers together, I get 0.41 kilograms times meters per second. But the question here says find the total net. Remember, that word total net means to add the momentum of after the collision with those soccer balls. So let's do that. 0 plus 0.41 equals 0.41 kilograms times meters per second. What the heck? Look at that. How freaking awesome is math? 0.41 was the momentum before the collision. 0.41 came to the momentum after the collision. That is proof of what we call the conservation of momentum. Okay, and we have a lab over this. We need to make sure that we can do this equation. The next part here says, how does the momentum before the collision compare to the momentum after the collision? They're the same exact number. What type of collision did the two soccer balls experience and why? Okay, so the type of collision is when I have two objects here and I ended up with two objects. So I started off with 2, I ended up with 2. So in that case, we call that elastic collision. But why is it elastic collision? I'm going to go ahead and put a comma. I started with 2 objects and ended with 2 objects. That's why it's an elastic collision. Alrighty? Not too bad? So we have a couple of practice problems up here, and they would like for you to go ahead and decide, well, what type of collision occurred in the scenarios? A piece of gum hits a window. Well, if the piece of gum hits a window, couple